The last kind of variation on a weak acid or weak base by itself, much more common with weak acids, is when you get into a mixture of acids or a polyprotic acid. In both of those cases, it means you have more than one thing impacting the concentration of hydrogen ion and hydroxide ion in solution. So it seems like you've got this really complex equilibrium where you've got hydrogen coming from here, hydrogen coming from there, two K values to deal with, one K impacting the other. And all of that's true to get down to the exact details. But the nice thing is, in most cases, we have one thing that's really impacting our solution way more than the other. So if we have a mixture of acids, what we want to look at is which of our acids is stronger. Sometimes it's a mix of a strong acid and a weak acid. In that case, the strong acid is the one that produces almost all of the hydrogen ion, and as a result is the one that impacts the pH most importantly. So focusing just on the effect of that strong acid really gets us close enough to the answer, or gets us what we need to know for the answer. Another common thing is when we have two weak acids, but one of them is significantly stronger than the other. In that case, the stronger of the two is the equilibrium we focus on. That one ionizes a lot, with the other one ionizing so much less that it doesn't significantly, once again, impact the pH or the solution itself. When we're doing this, we would think about it mathematically. That'd be great to do. You focus just on the strongest one. But we also have to understand what that means conceptually. How does that impact the ionization of the second one? So we've got examples down here, a stronger acid with a weaker one, and we would need to think about that weaker one in terms of Le Chatelier's principle or the common ion effect. If there's already a bunch of hydrogen ion from this first one, how much of that second one would ionize? The hydrogen ions may be shifting that equilibrium a little bit to the left, ionizing it less, and actually impacting how much of the anion is in solution. This is also true when we look at a polyprotic acid, and phosphoric acid is a great example of this. That was introduced in one of the first few videos when we first saw what a polyprotic acid was. Well, this breaks one hydrogen off at a time, but we can see very different values for K. You can do the math, and the practice problem does that to show exactly how much hydrogen ion is produced. But most important is also thinking about which ions are high in concentration and low in concentration. Since if we're talking about something that's weak, which is all of these down here, except for hydrochloric, that means that the unionized acid is way higher in concentration than any anions or the hydrogen ion produced by those weak acids. And then as I go to the next weaker thing, whether it's the second ionization for a polyprotic or whether it's the weaker acid of the example, that anion is lower in concentration than the initial thing. And then if we continue to ionize, the products of the successive ionizations are even lower and lower and lower. So when you watch this video, the problems for number 6, the math is good, but even more important than that is the conceptual idea of which things are really high and which things are really low in terms of their concentrations.